aerodynamics project, we were trying to find the horizontal distance of a ball after it impacts with the plane, inclined at 30 degrees. Our first step was to find the velocity of the ball that the instant hits the inclined plane right here. To do that, we use the conservation of energy, which states that during the motion of the sum of the particle kinetic and potential energy remain constant. So we chose to consider this ball a particle. So T1 is 0 right here because the ball starts from rest, so the velocity is 0. We chose our datum to be point D right here, so that it allowed for our potential energy to be mgh. The right side of our equation, right here, there's no potential energy, but now there's a velocity due to the acceleration of gravity. Our masses remain constant, so they cancel out. We plugged in our values and solved for our v-ball 1, which gave us 16.0499 feet per second in the negative direction.
And that's the velocity of the ball at the instant it hits point D.
Right there.
Yeah.
Then we use the coefficient of restitution, which is the ratio of relative velocity of the particle, separation just after impact to the relative velocity of the particle's approach just before impact. In order to completely solve for the coefficient of restitution, we needed to solve for the vertical velocity of the ball right after the collision with the board. To do this, we use the coefficient of restitution again, where in this case it's kind of the opposite.
You mean conservation of energy.
I'm
right?
sorry, conservation of energy. So in this case, we have our v-ball 2. Our
Prime.
potential energy is our v-ball 2 prime. Our potential energy is 0, and then our right side of the equation, our velocity is 0, and our potential energy is mgh. For this, we also had to do another little experimental value where we calculated the the vertical distance after the ball, basically the bounce up to the ball for the height. So if I were to drop this and it bounced back up, what that height was.
And the plane was completely horizontal, so there was no angle.
Horizontal plane.
Yeah.
So for after that, we plugged in our values where it allowed us to find our v-ball 2 prime. Once we found that value, we came down to our coefficient of restitution equation, which our v-board and our v-board 2 and our v-board 1, the boards don't change, they don't move, so these both go to 0, which allowed us to get to this point where we plugged in our values for v-ball 2 prime and v-ball 1, which then gave us our value of coefficient of restitution.
Plugging in the known values of v-ball 1 and theta to this equation will eventually result in the equation sine alpha is equal to 8.02495 feet per second divided by v-ball 2. The coefficient of restitution, which we solved for previously, is applied here. The plane of contact is oriented 30 degrees clockwise from the horizontal, so the line of impact is represented by the green dotted line perpendicular to the plane. Plugging in the known values of E, v-ball 1, and theta will eventually result in the equation cosine of alpha is equal to 10.6165 feet per second divided by v-ball 2. Dividing the first equation by the second equation will result in the tangent of alpha. Algebraic reduction results in tangent of alpha to equaling 0.7559. Taking the inverse tangent of that value results in the value of alpha, which is 37.0854 degrees. This alpha value can then be plugged in to either of the above equations to obtain the value of v-ball 2. We plugged it into the first equation and got a v-ball 2 value of 13.3083 feet per second. Furthermore, the angle between v-ball 2 and the horizontal, which we named beta, can be found by utilizing geometric rules. Theta, alpha, and beta are complementary angles. Therefore, subtracting theta and beta from 90 degrees results in the value of beta, which we calculated to be 22.9146 degrees. The next step involves finding the time it takes for the ball to bounce to its maximum height. This kinematic equation is used, focusing solely on the y direction. When the ball is at the maximum height, it is momentarily at rest. Therefore, the final velocity in the y direction is equal to 0. The initial velocity of the ball in the y direction is simply equal to the y component of v-ball2. This is represented as v-ball2 multiplied by sine of beta. The value of gravity is given as 32.2 feet per second squared. Plugging in these values and solving results in a time value of 0.1609 seconds. The ball takes 0.1609 seconds to reach the maximum. Therefore, the ball also takes 0.1609 seconds to fall from the maximum to the point directly horizontal from point D. Therefore, the time it takes for the ball to travel the distance from A to B is equal to 2 times 0.1609 seconds, which comes out to be 0.3218 seconds. This next kinematic equation is used and focuses on the x direction. The initial velocity of the ball in the x direction is equal to the x component of v-ball2. This is represented as v-ball2 times cosine of beta. The value of acceleration is 0 because there is no acceleration in the x direction. The time it takes for the ball to get from A to B is plugged in for the t value. Plugging in all of these values results in the value of the length of AB, which comes out to be 3.9447 feet. Now that we have the length of AB, we now need to find the length of BC. Kinematics is also used in this venture, with the equation examined in the y direction. Here we're trying to find the time it takes for the ball to fall from the point directly above point B to point C. First, the datum is set as a horizontal line passing through the point D. This allows for correct signs in the following calculations. Given the location of the datum, and also that point D is 1.83 feet above the ground, which was measured using our measuring tape, the value of D is negative 1.83 feet. The initial velocity in the y direction is in the negative direction and equivalent to the y component of v-ball2, which is represented as negative 13.3083 sine 22.9146 degrees, and this is in feet per second. The acceleration is equivalent to the acceleration due to gravity, which is given as 32.2 feet per second squared. This value is negative in the calculations since it is directed in the negative y direction. Plugging in these values results in a quadratic equation. Inputting it into a graphing calculator results in two time values. The first one being t is equal to negative 0.5369 seconds, and the second one being t equals 0.2130 seconds. For the rest of the calculations, we're going to be using the positive time value. The t is equal to 0.2130 seconds value. Now that we have it, we can then plug it into the second kinematic equation to find the distance from point B to C. This equation is examined in the x direction. The initial velocity in the x direction is equal to the x component of v-ball2, which is represented as 13.3083 times cosine of 22.9146 degrees, and this is in feet per second. The acceleration is equal to 0 since there is no acceleration in the x direction. Plugging in these values results in the length from point B to point from point B to point C to be 2.6110 feet. The total length the ball travels, which is the length from point A to C, is equivalent to the sum of the length from point A to B and the length of point B to C. This theoretical value is calculated to be 6.5557 feet.
Alright, ready?
Ready?
The experiment resulted in the length of AC to be 5.33 feet. Plugging in the theoretical value of 6.5557 feet and the experimental value, which we just found, of 5.33 feet into the percent error equation and solving it results in a percent error of 18.6967%. There are several possible reasons for this error. The experimental value is smaller than the theoretical value, so there has to be some type of discrepancy between what we were planning to do and what actually happened in the experiment. So the first possibility would be that the ball may have been dropped at a height not exactly equivalent to 4 feet. So since the theoretical value was bigger than the experimental value, one would think that maybe during the experiment we dropped it at a height lower than 4 feet, which would have made the total distance it travels horizontally smaller. And the second possibility would be that when dropping the ball, a rotational component may have been added to the ball, which would affect how and where the ball bounces after impact. For example, there could have been a backspin added to this ball. But overall, the percent error of 18.6967% is relatively small for this type of experiment. And overall, this project has taught us a lot in regards to conducting experiments and calculating out what we predict will happen. So overall, this was a good and informative experiment.